Good. So yeah, let's get started. I'm really happy to be here. It's an unusual setting, and I don't get to see your sweet little faces in front of me, so I'm kind of missing this. But anyway, let's go. This is the kind of thing I want to program with, like nice little bricks, like beautiful little bricks that I can assemble to make beautiful and complex objects like this one, right? That is something I would really like to be able to do. And I'm not kidding when I'm saying this, because this is how we teach kids those days to how to program. That's the Scratch environment from the MIT. And as you can see, you can see some bricks on the screen, and there are even some more complex bricks like a repeat or forever. And some of those bricks can also be parameterized, have some parameters. So that gives kids an intuition how to build software by assembling stuff together. Unfortunately, life is often more complex than this, and my day-to-day job looks a bit more like this. Like, things are messy, things are hard to align, things are kind of complicated. I need to have the steel ball to roll exactly at the right place to eventually go to the right destination. So life is complicated. So today I want to talk about things that makes life easier, and in particular modularity. And why it's important to have modularity in our systems, what is important to have, whatever you call them, components or modules, and how they can make our life easier. So why do we care about modularity and modules? And I think there are many reasons why we care, or we should care, about modularity and modules. The first reason is that it's really a great tool to help us reduce the complexity in our systems. It's very easy to start from a small application, a small service that does a little something, and quite rapidly add more and more requirements and get totally overwhelmed by everything that's going on. It's very easy to get there. So components and modules, they help reduce this complexity by bring isolation to the system. And that's a strategy that's employed in software, but that's, of course, a strategy that's employed in many other physical systems as well, like in a tanker like this one, for example. You don't put the oil in like a huge, large tank, right? You have small compartments inside the tanker. So if there's any one of them that's leaking, you will not have all the other ones being affected, right? And this also has like some interesting physical properties, like on the sea is rough. Because you have small tankers inside, the liquid will not move all around the ship. So your ship will be a lot more stable. And of course, there's a trade-off here, right? Those nice properties, they come at a cost. Now you need to build all those compartments inside the tanker. But overall, there's a huge gain in being able to isolate stuff. And you find this in software. There's a cost in thinking about those components and designing them. But at the same time, they prevent failures to propagate to the rest of the system. They help you keep local things really stay local and so on. So they are really an essential tool in managing the complexity we have in software. The other thing where it's really helping us in terms of complexity is in how we understand our systems. If you take a system like Windows 10, for example, it has something like 3.5 million files. It's in image. You cannot think about those files. If you start reading them one by minute, you will spend like 25 years of your daily working life just to be able to read all of them. It's just not possible. On the other hand, you can still understand a system like Windows 10 if you're presented with the subsystems that it's composed of, right? And you understand how they interact with each other. A bit like this engine, you can see that there's a cold section, there's a hot section, and you understand that maybe the cold section sucks the air in, and the hot section is going to expand it. And then you can drill into each of those sections and understand exactly how they are doing their job of compression, exhaustion, and so on. Because the previous picture is, you cannot understand it all at once. And it's the same with software. If you have carefully designed systems, you will at least get some information of what the system is doing just based on this on the overall decomposition, if it's done properly. And that will be really, really helpful in understanding what the system does overall. So that's useful. And there are plenty of other advantages of having modularity in modules in a given system. Another of those advantages is that they really help us organize our work. As soon as you start working in a team, on large software, you have to organize your work around the software. And there's this law named Conway's law, where Melvin Conway observed that many products that were effectively delivered were closely mimicking the structure of the team producing them. And there's this saying that if you have a team, like if you have 4 teams working on a compiler, you will get a 4-pass compiler. And it kind of makes sense. And what Conway was saying is that, okay, maybe we should start by having a look at the product itself, try to understand really fundamentally what are the different parts, what are the different components of the overall system, and then based on those relationships, then build our teams to mimic those fundamental relationships. And to give you a concrete example of this, there's this company called Childlike. And they have this blog post where they said, okay, we decided to rewrite our full system. And first of all, that's something where you should say, no, don't do this. You should never rewrite totally your system, right? It's generally not a good recipe for success. And they wanted to go from a system having Scala, Hadoop, HDFS to something using Postgres and Haskell, like something totally different. But they motivated it and they explained exactly how they went about it. And one big ingredient in their success was that they were able to draw out all the dependencies between the different components of their system and know exactly by which component they would have to start in order to not disturb the rest. And then they could lay out a very precise migration plan from the old system to the new system. So being able to control all those components and all these dependencies is really an incredible enabler in having people working and coordinating around software. Yes. Then we have other advantages that are more like economical. It takes lots of effort to develop software components. You have to write the code one time, sometimes 2 or 3 times just to get it right, write some tests, some documentation, and so on and so forth. It's a huge effort. And if we can reduce that effort, it's even better. Again, you can see this trend in the industry. So for example, in the alliance between Renault and Nissan, for the first year where they were able to launch the same line of family of vehicles together, they made something like 3 billion worth of synergies, 3 billion euros worth of synergies based on that. So as a customer, you think you're buying a Nissan or you're buying a Renault, but actually internally they share many of the same components and they have well-defined interfaces and protocols and all the things we know when we write software, right? And so it's a huge economic gain to be able to just reuse components across bigger systems. And of course, in software, we've been doing that for a long time now, but we are doing that more and more and more. So if you look at this presentation by Heather Miller, you will learn that more and more companies, almost all the companies nowadays are using open source, which is a great thing. I mean, that's really being able to put in common lots of knowledge and lots of work. But also, if you look at the presentation, you will also learn that it's a bit scary because some of those components shared by many systems around the world, like critical systems, are maintained by like 1 or 2 persons only, which is kind of scary if you think about it. But there's a huge economical advantage in being able to reuse and share components that are well crafted. Another aspects of being able to have modularity and components that are easy to assemble and really readily available is that it really helps with your creativity. Many times you're in front of your laptop and you have an idea, okay, what would happen if I would just put a cache here? Would I just improve my performances or not? By how much? And being able to do this like in 10 minutes or 20 minutes without having to jump through all sorts of hoops to rewire your system, to change your configuration files in so many places and so on, that's really helpful because there's a huge opportunity cost of not being able to do that. If you're not able to do that, you will not even try it. You will not even try your new idea because you're thinking, oh, it's going to take me the next 2 days just to be even being able to think about it and to experiment with this idea. So that's really a loss. So on the paper, this looks all good, right? I'm hoping that many of you are just nodding, saying, okay, yes, yeah, of course, modularity is really nice. But do we have even studies proving this, right? Was it really studied? And there are a few studies which you can read on the effects of modularity on systems. So there's one of them that was done 2 years ago on software quality. And it is indeed showing that there's an improvement in maintainability the more modularity you have. And it's an interesting study because the details, as in many studies like medical studies or psychology studies, it's always interesting to look at the details. So you can have a look at the details. One detail that I found interesting about this study is that it's not only about modularity, because those good results, they were obtained for Python. And if you do the same experiment using Java, you will not get such good results. And the people doing the study, they said, oh, well, maybe modularity is not the only thing that brings good maintainability. And they made an hypothesis that, again, needs to be proven, that maybe Java is not a very expressive language. And expressivity is also a very important factor in maintainability. But, well, okay, now we have two factors we can consider, expressivity, but for sure, modularity is certainly an important factor in having maintainable and quality software. So this all looks really good. Lots of good properties of when you have modular systems. But on the other end, it's hard to get there. It's really hard. So today I want to list a few of the reasons why it's hard to get there and what gets in the way. What are the things we should look for? So maybe I want to start with a little rant about why it's hard. And it's of course hard if you don't care about it, if you're in denial about the need for modularity, the need for modules, the need for components. And you can find many people using functional programming thinking that modules are not important anymore. Modules are not necessary. So I want to talk about this today and have a little rant about that. Because even if you're using functions and you think they are the best thing in the world, many of the functions you're using are not living in total isolation. In many places, they come in pairs, they come as a group of functions to do something. And sometimes they only mean something if they are weighted against one another. I mean, you don't really know what's the effect of adding a new member to a group, unless maybe you can list all the members of a group and stuff like this. So they are really intertwined together. They don't really live apart from each other. And this group of functions makes sense together as a module that needs to be maintained and evolve, that needs to evolve separately from the rest of the software. But that's not the only thing. The other thing that you find in some functional programs is some functions like this. So you say, okay, I need to decrypt some values. And in order to do this, I'm going to log some stuff because I'm doing some important stuff and I want to make sure what I'm doing is logged somewhere. And also maybe the encryption is kind of hard and it takes some time. It's not very performant. So I'm going to cache some of the results in my database so I can be faster in retrieving some results right away. The stuff has already been decrypted. And of course, I need some decrypting capabilities, some cryptographic capabilities. So I need a logger, a database, a decryptor, and then I have my encrypted values and I can decrypt them and I get decrypted values and it's all good. But the thing is, so you see this kind of a function written in different styles. So this is in Haskell where we are very explicit in everything we need to do this decryption. This would be using the MTL style where you have some monad constraints to denote the kind of capabilities you need to do this. Or this is almost the same thing, but now grabbing those capabilities from an environment, E, using the ReaderT pattern. But eventually, those are more or less the same way of writing the same thing, right? And this function has a signature where not all the parameters are totally equal. The first three parameters are only about providing dependencies and stuff that's useful for your implementation. That's not necessarily has to be seen from the outside of the world. I mean, as a client of that function, I don't really care if it's using a logger to log stuff that it's been doing for later usage. I just want my decrypted values. And one of my main issues with this style of programming is that it totally breaks encapsulation by considering that all parameters are equal. So we will come back to this issue later. And one more argument in my last argument for functional programmers and modules is that even in the language for like Haskell, there are modules anyway. If that's a typical piece of Haskell, but if you open that file, you will see that at the beginning of the file, there's a module declaration, and then you have some imports from other modules, and you have things to set up the visibility of what you want to import, of what you want to export. And so even a language like Haskell found it really useful to have the notion of module. And actually, it's a kind of a weak notion of module. We can do a lot better than this. So that's the end of my rant for now. I think modules are important. I think we can still do nice and important functional programming without side effects and still find a very good use for modules to build large software. So now if you think about modules and components, what is hard in finding out what are those components? Well, the hard thing about finding out the right components is that what you want to do is have the maximum isolation possible. So you don't want every component to talk to every other component, right? You want to minimize the paths of communication between all those components. And that's hard to find out. And not only it's hard, but it's something that's going to evolve. As you understand more and more about what you are doing, as you're getting more and more requirements, you will have to reorganize your system. You will have to reorganize your components to split some interfaces and do things like this. But that's the kind of growl you're looking for, is this thing about having high cohesion inside a component, things they can talk together really freely, and low coupling, like the minimum number of dependencies on the rest of the world. And in particular, what you want to avoid is what I call the butterfly effect. You really want to avoid in your component graph to have like one component being in the middle of everything, because that component is going to break your system very frequently. That component has many reasons to change because it depends on many other components. And in turn, if that component changes, it can break many other components. And sometimes you find this kind of effects when you're using a utils component, where you can put everything that you think is kind of non-essential, but brings with it lots of different dependencies. And I call this the butterfly effect because it's a bit like in a weather system, when you have, they say that you can have because the weather is a very chaotic system, they say you can have a butterfly in Singapore flapping its wings, and then 3 days later you will have a tornado in Texas, just because it's a very chaotic system. So those components, they can play the role of butterflies. And the hard part about finding out the good components and dependencies is avoiding those kinds of butterfly components. And the other thing that's kind of hard with dependencies is that finding out dependencies is not always obvious. So there's this movement or website, there are a few presentations about that, called connaissance, which means basically to know about something else. And there are some very obvious dependencies that those people have listed. If you import something, I mean, if you import a function, you depend on that function name, right? If the name of that function changes in a further evolution of the package, your code might break. So if you have a language like the Unison programming language, trying to get away from all those dependencies of names, for example, where under the underlying implementation of Unison makes you rely only on the hashes of the code and things like that, and that's very clever. But there are other dependencies that are more subtle. Sometimes your code will not work if another piece of code has not been executed before. And that's what you find sometimes with mutations and side effects, right? If you read something from the database, someone has to have written that thing in the database before, right? And you depend on this temporal condition. And that's kind of a hidden dependency at this stage. It's not reflected in your types or in your imports. Other types of dependencies is like some data sometimes has a real strong meaning. You might receive, I don't know, a card, a Visa card number that's made made up of 9999s, and that number is supposed to mean something for your software that's been precisely configured to react with a specific behavior just for that single piece of data. Again, that's a dependency that you have on something else producing that exact piece of data. And it's really hidden because you don't know that from the types, right? So the hard part about finding out what are those dependencies is understanding what they are and make them as explicit as you can, reflecting this in types if you can, for example, or getting rid of side effects if you can. And when you think about dependencies, you're trying to avoid as much as possible drilling down into dependencies. So there's this thing called the law of Demeter, saying that you should avoid going very deep in terms of things you depend on. So for example, a car doesn't have to know that the throttle can accelerate. It doesn't have to know that. Maybe you can just code up so that the car just wants to speed up. And then the speed up implementation will know how to do this because the speed up implementation will know how to talk to the engine and so on. So I encourage you to have a look at this website to learn more of this kind of classification on dependencies. But unfortunately, that's just the beginning of the problems here, because even if you have nice components and you more or less understand dependencies between those components, if you have a complex system, there will be large chunks of the behavior that will just be emergent behavior. That will just be, once all the components are interacting together, they produce something useful. And it's only by understanding all the dynamic behavior, all the dynamic interactions between all those components that you will understand what the system is eventually doing. So understanding all the static dependencies, unfortunately, is still not the graal for this. It's still not the silver bullet. There's still more work that's necessary to understand how all the modules work together. Another thing that also does not help us in, for example, reusing those components is that most of the time we don't have specifications for components. Nowadays, and especially maybe in the Haskell or Scala community, we are lucky because people are writing more and more tests, and especially properties tests. So by reading the tests, if they are really thorough, you can get a better understanding of what a component or what a piece of software is supposed to be doing. But it's rare that we do this really religiously for all the things we are developing. And not only it's rare, but sometimes even the thing that those components are supposed to implement, like the very specification of what they're supposed to do, is not even tested. We don't even know if the specification of what the thing is supposed to do does even make sense. And so you have now languages like TLA+. So that's the one that I'm showing here, but there are other languages. The other one is on this screenshot is Alloy, which is more suited for domain models. That can be used to write specifications, even just for the behavior, even without considering the implementation that's going to follow, just at least what's the specification of what your component is doing. And most of the time, we don't have this. So it's very hard to reuse something where we don't fundamentally know what that thing is supposed to be doing. Well, to just make an aside, even like many programming languages don't have a separate specification, for example, or it's very shallow, or that specification is not really machine checked, for example. So it's just a bunch of rules that are supposed to be true and coherent with each other. Okay, so that's one thing. The other thing is that now imagine that you have nice components, you understand their dependencies, you try to reduce the dependencies between those components. But as I said before, those components, they still need to communicate with each other. So they still need to exchange some data. When you have some functions, they take some parameters. And the parameters that they take can be some very simple types like int or string, but sometimes they can be some more complex types like customer, invoice, routing things, payment, and whatever. And that data is, in a way, another component that in its turn is shared by all the components that need to talk together. And in a way, we end up with a new butterfly component. We have some definitions that all of a sudden are being shared by everything. So if you don't get those things right, everything can break. And this is really a problem. The data is really infectious. That's something that you have to get right almost immediately. Let's take a concrete example about this. I found this proposal, which I loved. Someone proposed to have to refactor the calendar so that we have 13 months in a year, and all months have an equal number of days. And it's kind of fantastic because you always know that Mondays, they fall on the 2nd, 9th, 16th, and 23rd of the month all the time. It's very regular. It's fantastic. And there's even one day that's like free for everyone, like New Year's Day. It's a special day, and it works like this. So it's kind of a nice idea. But at the same time, can you imagine taking this idea and implementing it in all the systems that you have around the world? It's like, it's crazy. The amount of work that would be necessary to just implement this is not worth the supposed gains that you would get out of the more regular calendar like this. It doesn't make sense. And you find other issues with data in how it evolves. And most of the time, data has to evolve. One aspect of this that you can see in some presentations is the so-called expression problem, where you take a data type and you show that it can be hard to add new variants of this data type without impacting the functions that are using this data type. And many times when you see talks presenting this expression problem, you have small examples of this thing, like using, for example, a small lambda calculus or some arithmetic operations that you want to execute or print out to the console, things like this. But unfortunately, there are real examples of this at large, like in big companies. And to give you an example of how extending data can be hard, when I was working at Zalando, Zalando started by selling shoes and clothes, t-shirts, shirts, and whatever. And they had this data model like this, where you had the idea of a model of a shoe, and you had different so-called configurations, so one per color. And for each configuration, you had different sizes, right? So this kind of a data model, like a tree, like this. And I mean, it's all good. You can grow a full company based on this. And that's what they did. But then you grow the company even more, and you want to add more information to this data model. So for example, you want to know who is talking about this particular model of a shoe, like the yellow Nike in the picture. So you want to reference more information in that data model. And actually, you don't want to sell shoes anymore only. You want also to sell cosmetic products. And how do cosmetic products fit in that picture? They just don't fit. It's just not made for them. So what can you do? Can you really extend this model? And at Zalando, they decided to not extend this model and build a brand new one. So now I can let you think about what it means at the level of a huge company of something like 12,000 employees. Rebuild your entire system based on a new data model that encompasses the old and adds new generic fields for everything. It's kind of a madness. And as far as I know, this migration is still ongoing, and it started 4 years ago, I think. So extending data is really hard because it's so infectious. It's everywhere. It's very hard to make data modular. That's what it means. Another thing that's making modularity hard in terms of systems is that even if we are very careful to program using functional programming to get rid of side effects locally, and we are reaping lots of benefits out of this, we still have mutable states. And that's really annoying, right? We are still writing to databases. So we still need to take care of which process is writing what information when. And that makes our systems at large less modular than they could be because of this. That's a problem. Another problem about modularity that people don't talk often very much, but which I find is very real, is that we have ways to describe components, basically based on the idea of having interfaces, implementations, dependencies, configuration, specifications for those components and so on. But the way we describe how those components are being assembled, are being wired together, is very ad hoc, is very unprincipled. There's not really a language to describe this, and you can find all sorts of mechanisms to talk about assembling components together, and we should have a language to do this. I mean, if you consider components as forming a graph, we should have a language where you can say, okay, now take the previous graph and just replace the component at the top. And probably that's not too hard to say, but you should be able to say, okay, now take this one in the middle, but split it in two and have different components talking to the different two components that were splitted. Or you want to say maybe now, okay, change all those components that can be anywhere in the graph, but if they have this specific type. And that's something, we need a language to do this. And we don't have a language to do this. And that's very annoying because this problem actually happens. And let me give you a concrete example of where this happens. In build tools, so build tools, no one is really happy with build tools, right? People find build tools are horrendous. SBT is wrong, Maven is wrong. Well, Gradle is not better than Maven. Let's go back to Maven. In the Haskell world, people are fighting over Cabal and or Stack all the time. And even if you try using Bazel to rule all the build systems, well, it has also all sorts of problems. But okay, creating a build tool is difficult. There are all sorts of concerns that you have to consider when you're creating build tools. And this is a difficult task. I understand that. But one concern, one thing why I think it's difficult is that we don't have a language to describe how to wire things and how to rewire things. And to grab an example from a presentation on some of those tools. So there's this tool for Scala called CBT made by Christopher Vogt. And in the presentation for this tool, Chris shows that for many operations that you want to describe in a build tool, you have a graph of tasks and settings, and you want to derive that graph into different graphs where, for example, in one part you say, I want to change my Scala version to be 211 and have almost the same graph with 212, right? And what Chris is using to do this is just piggybacking on Scala as a programming language to be able to override, to manipulate this graph. So he's using inheritance to say, okay, now override this setting that's being inherited by changing the value. But because he's reusing some mechanism, which is inheritance of implementation, that was not primarily done to do graph manipulation, it falls short in some cases. And you can see Chris wondering in this presentation, well, isn't inheritance hard? And eventually giving the same kind of advice you have in Java programming books, like, oh yes, but maybe we should use composition because composition is easier in other places. But then if you use composition, you lose the ability to override stuff whenever you can. So there's kind of a trade-off here. That's really annoying. And I think the trade-off comes from the fact that what we want is a general language for wiring stuff, and we don't have it. So we're piggybacking on something we know, which is overriding methods in a programming language. And I'm sorry, because I'm bringing bad news, but there are other issues that this time get in the way of reuse. And this is obsolescence. When I started my programming career, that's the tech stack I was using, Java, J2E, CORBA, Oracle. And I mean, life was in a way quite simple, but then there was a revolution, HTTP, and then the interfaces had to be produced with SOAP, and then it changed all over again. Now I had to use REST and JSON. So all those carefully crafted services with SOAP had to be rewritten all of a sudden with REST and JSON. And that's really annoying, but it's not the end of it, because then you have many different ways of storing your data, not only in Oracle, but all those NoSQL databases with all sorts of different properties and distributed computations and so on. And then you have big data, and you have even more way to store and access and process your data. And then, oh, you have this flurry of programming languages. And it looks like every 5 years you have a major programming language arriving on the scene. And in a way, it's a good thing. And this has been enabled by Dockerization and the fact that it's easier than ever to share code amongst people. And I really view this as a good thing. We can really make progress in many ways. But at the same time, all the hard effort that we've put into building components for those technologies, for those languages, now it goes out of the window. We have to recreate them all the way. Like, take a very concrete example. ZIO is recreating a full ecosystem based on the ZIO way of doing things. It's nice in many ways, but it's also lots of effort to be able to come up with a new ecosystem for all of this. And that's not the end of it. We are going to have more and more of this. I mean, for example, we're just at the end of a huge period of time, maybe 10 to 15 years, where we discovered that we could not go monocore anymore. We had to go multi-core and do many more things concurrently with asynchronous programming. And we had to come up with ways to program and sometimes add new primitives in our programming languages, like sync and async and wait in our programming languages, like in C#, or to come up with support in the form of monads to do asynchronous programming and so on. And now we are getting used to that. It took a long time to get there, but now we are kind of mastering this. But we have other revolutions coming up. So for example, if you read this paper, you will see that one very core assumption that we had about processes was that CPU was always faster than IO. IO is slow, CPU is fast, do things locally and stuff like this. But it turns out that now in data center, IO is really, really fast, and you can saturate your CPU much more than you can saturate your IO. And that means that we are going to have to rebuild whole operating systems to just take advantage of this, and brand new components just to take advantage of this. So to me, it feels a bit tiring that we have constantly to rebuild the world all the time, and we cannot reuse everything as we wish. So there are many reasons why modularity can be hard, why reuse can be hard, and we need to fight this, right? But fortunately, we have tools to do this. We have ways, we have more and more tools to do this, and we even have old tools to do that. So today I want to introduce some of those tools. And before I'm talking about some more recent tools, or maybe even some research about modules and modularity, I want to go back a bit and quickly around the history. Where do modules come from and where they were invented? So it's going to be short. I will not tell about everything, and it's probably not going to be so precise, and the dates, I don't really guarantee the dates, but let's go about it. So in a way, you could say that modules were invented in the 60s, like in Lisp and Algo languages to step away from the machine, to get more abstraction from the machine. And it's kind of funny because at the time where people introduced procedures like this, other people said, oh, you cannot do this because there will be some details that will leak in your nice abstraction. You cannot abstract code like this. We still need to program in using assembly at some stage. And fortunately for us, that's really not the case anymore. We were effectively able to encapsulate lots of things. And it's quite rare. I mean, it's not quite, I mean, there are some really specific situations where you really have to wonder about how the machine is going to run stuff if you really want to be performant. And you can leave this to libraries to do this. But most of the time, unfortunately for you, you can reason at a much higher level of abstraction by encapsulating lots of small details into procedures. So that's what procedures brought at the time. In the same decades, people came up with objects. And I want to mention this because the language coming up with objects was really intending to use objects not so much as a way to reuse code, but more as a way to simulate, and that's where the name comes from, simulate physical systems or systems where different elements or agents are interacting together. And the idea was, okay, can we have some nice representations on how the things are going to interact together? and be faster in simulating complex systems and understand how they behave. So the idea was a lot more about simulating and system understanding rather than reusing code or making sure that things were really modular. Maybe you can turn to languages like Modular and Modular 2. For the first languages, really thinking about what it means to build larger systems and what it means to really hide some parts from the rest of the system. Where I'm hearing some notifications. I hope I don't have to answer messages in important messages. Okay, let's not break encapsulation. I agree. Oops, sorry. Oh, I'm messing up with my messages. Coming back, yes. Yeah, so modular was the first to introduce the dot notation, for example, where you could say m1.p to access a given member of a given module, and they even introduced this idea of having a module interface, where you would just declare a bunch of properties or members that are available in a given module without necessarily exposing their implementation. So the people behind the modular programming language were all about scaling systems up by hiding some implementation details. And in a way, you find this same thing in a language like Ada, where you also want to hide. This time it's more like modularity in the small, where you want to have abstract data types where you can hide the concrete implementation and being able to reason more in the concepts of your domain. So for example, you can talk about calendar dates and days and hours without showing up the fact that they are being implemented using integers. And you don't expose integers because maybe you have a better or more efficient representation. Or maybe you consider that people will like to program after year 2100, right? Programming doesn't have to stop after year 2100. Things like this. And then years later, you come up with some real nice module systems and module languages in the form of standard ML. So in standard ML, you have nice notions of interfaces in terms of so-called signatures, where you can have type parameters, you can have lots of function definitions here. You can declare types that you're exporting from a module. I found out that you can even declare exceptions that your module is exposing. So it's interesting to see that exceptions are not being declared at the level of each function, but declared globally. Once you open your module, you know that you will have to deal with this kind of exception. And then you can provide an implementation for this kind of structure. And the cool thing about SML modules is that a given structure can implement many different signatures, and a given signature can be implemented by different structures. And it's a very structural typing system, because it only depends on the structure of the types for the signature and the structure on the types in the implementation to be able to use a given structure anywhere. So that's really nice. And then came the dark times. So you would think that SML was like the state of the art and everyone would be using SML from now on, because it's so nice to have good grounded notions of modules, components, and implementations. But at the same time, in the 80s, we had a need to develop a lot more code, like a lot more code. And OO was really a prevalent idea at the time. And for many different reasons. Some are very cultural, but some of them are kind of also related to this idea of modularity and abstract data types. Like the idea that possibly having objects is a good way to encapsulate behavior. So maybe we can grow full systems based on the idea of objects. And people ran wild with it, but very soon realized that we still had issues with modularity. It was not solving everything. So one of them was multiple inheritance, like in C++, for example. And people coming up with Java realized that there were issues with multiple inheritance because of the so-called diamond problem, for example, and decided to get rid of multiple inheritance. People in other languages like FL provided better tools to deal with multiple inheritance. But even single inheritance can be a problem. So if you have such an inheritance tree, you can still have issues because of dependencies. So you can have a subclass relying on some behavior declared, implemented in the superclass, right, to do his behavior. But at the same time, it's also possible in the superclass implementation to delegate some of the behavior to subclasses. And now you have a catch-22. You have different implementations effectively depending on each other. And if you have this across different layers in your object hierarchy, you can end up with something that's totally unmaintainable because you have all those kind of circular dependencies in your tree. That make things really difficult to deal with. And as people grew systems, they realized some needs for more modularity and tried out some new ideas. So for example, if you want to trace all the calls around the system, and that's a very common need to be able to know exactly what was called at a given time and maybe record how long it took to call a given function and so on. It's very tiring to write all those things manually inside your language. So people try to go meta and go outside the language to use aspects, for example, to record this. And it's a clever idea. And at the same time, the implementation is very not maintainable. It has all sorts of problems. Because you go meta, you need to have other tools. In your compiler tool chain, now you need to inject more tools that you can see on this picture. And if you can see how the code is being referenced, it's being referenced using pure strings. So you have strings representing package names. And all of a sudden, if you refactor your packages, the code might compile, but at runtime, you will have exceptions because your aspect does not understand what you do anymore. So aspects were an interesting idea, but in a way that could not work because it was not integrated enough with the programming language. Another idea that was used was to double down on objects. So if objects are so good, maybe they should do more. And that's kind of the idea with EJBs. Can we do more with objects? Maybe they should be able to persist themselves. Maybe they should be able to talk to other systems. And so people tried that. And that led to a big problem, which is just conflation of concerns, trying to cram too much into one entity. And I mean, I've personally been on such a project, and it was a huge failure. It was not performant. It was hard to evolve and so on. And the practicalities of describing those objects with all sorts of XML configuration files, that was really horrendous, really hard to deal with. And after this came new ideas like Spring. Can you go, okay, maybe we should go back to simpler Java objects. But again, we still need to have a language to know how to wire things together. And maybe you can still use annotations and go meta again to do all of this. And the trouble with annotations is that if you put this idea too far, you end up with issues about, okay, how do they interact together? What does that even mean to add up all those annotations on top of each other? Are they exclusive? Is the order important? And there are all sorts of semantic issues if you do this. And by the way, there's an excellent blog post by Adam Warski on the subject, if you want to know about all the issues with using annotations like that. And where's the, oh, here it is. That's kind of the important part, right? That's the interface I want to test. So yeah, annotations were something that I think was used to try to solve an important problem, and we will talk about that later, but I don't think it was the right way to do. And then we have the realm of dynamic languages. And at first, they seem wonderful because you can do whatever you want. You can be very, very flexible. And if you take Ruby, for example, and the web framework in Ruby on Rails, it looks very, very magical because you can take the base object and add all sorts of capabilities at runtime on that base object. And then you can persist it to the database because you decided that now it was persistable to the database. But at the same time, it's actually a nightmare to understand what something is doing at a given time. And I mean, I really applaud of people who can deal with such systems at scale and really understand what it's doing. And then I suppose they need lots and lots of tests and lots of care to understand what's going on. Because I personally don't think this kind of idea really scale. So where do we go from there? So we see quite a rich history of understanding the need for encapsulating things, trying to find support in programming languages or meta programming for doing all of this. And today we have even more tools to try to do the same thing. So I want to talk about those new tools, and especially since we have functional programming and how it's linked to functional programming. And at first, those tools might seem a bit scary, right? Because some of them, they can use lots of abstraction. And what I want to do today is show you that actually we might not need all of this abstraction. And I'm going to go very contrary to the previous talk by Pavel. And I would like to have an interesting conversation with him after my talk to contrast things. Because I want to talk about effects. But before we talk about effects, I want to come back to simple things. I want to talk about what's important. So before we try to use smart techniques and smart abstractions, I think the important thing is still to control dependencies. For any kind of large system that you have, what the system means and how you package the concept in your system is what's going to dominate the most. It's what's going to have the most influence on your system and if it evolves well or not. So having a basic idea of what is an interface, what is an implementation, and making sure you can enforce this is really at the heart of everything. And if you're in doubt about how you should decompose your system, you can turn to this old paper from the 70s about what's the best way to decompose your system. And this paper advocates that you should try to look for things that are going to evolve. It's not so much about things that are being done right now, that have some kind of logical decomposition about my process is A, then B, then C. It's more about, okay, what are the parts of my system that are going to evolve and that I can hide because the details are going to be unimportant. That's what the service they provide that's important. And in Pavel's example are really nice about that, about what you might want to encapsulate the fact that you're using FTP, for example, to grab some information, because using FTP in a way is not important. The type of information you're getting from a subsystem is what is important. So to do this, we really need to think about domains and also resist the urge to cram everything that you don't think is in your primary domain, cram it into a utils component, because it does not belong here. And I mean, many of us, we are primarily working on one domain, like building a blockchain for something, building some software for a travel agency where we're thinking about customers, thinking about travels, programs, whatever, destinations. But sometimes we have to deal with lower level concerns like text manipulation or HTTP or database calls. And it's really useful at this stage to change your hat, make as if you were a HTTP library author. How would you provide the best HTTP interface for the rest of the world, or at least for your system to use? And how would you clearly separate this from other considerations? So it's nice to put, in a way, the DDD cap on when you're writing your software and being able to switch hats to get another hat. And something that can help with this is try to visualize the dependencies in your software and find if you have any hotspots, things that many components are depending on and that have a large interface, for example, and try to minimize those things. So this is an example of presumably a small service that we did on a previous project of mine, but we had a way to visualize all our components and all their dependencies. It was a nice way to see how things were working. The next thing is about, so once you have this, try to think about your components as a librarian. How can you label them? How can you store them? How can you document them? How can you ensure they can almost live in isolation as a separate, nice piece of functionality? And it doesn't take a long time to do this, but it's really useful to be able to do that one component after the other. Shannon, I need to check on my time because I think I don't have a lot of time left. Is that right?
You've got about 5 minutes left.
Oh, so I'm totally over time about what I was supposed to tell you because I didn't have a timer on. I'm sorry.
Oh, it's all right.
So I'll try to go quite fast for the rest. So unfortunately, I have to go fast on this. And I want to talk about effects for modularity. And especially in functional programming, we have different ways of doing this. Monad transformers are about modularity, as you can see in this title here. But the big issue with monad transformers is the stack you need to provide is very inflexible. And it's hard to write tests for it because it's hard to change how things are being implemented. And people came up with algebraic effects to have this idea that you could extend your monad. And this is the thing that Pavel showed earlier on with an F monad or free monad where you can do this. Unfortunately, for my taste, it's quite heavy in terms of types. You have lots of indirection in your software when you try to navigate into the code. And it can be also hard to rewire. I can talk more in details about this because I have first-hand experience about that. And it has other effects. It can be hard in terms of higher order effects using other effects. Then you have the so-called tagless-final style, which is a bit frustrating for me because it's now a rant and a rant and a rant. That's, I really encourage people to come back to the paper, read it, and it's a lot more than what is described usually in blog posts. And one issue with the tagless-final style is that it relies on type class, again, as a language providing mechanism for wiring stuff. And type classes in Haskell or Scala can be quite inflexible in how you can rewire stuff. So people, for example, in the Haskell community came up with another way of doing things using the ReaderT design pattern. And this one has other issues, which is mostly the ReaderT design pattern only allow you to replace low-level dependencies in your graph. So it's kind of good for small systems, but in my mind, that doesn't scale to larger systems where you want to replace whole layers or whole groups of components all at once. And if I can say a few words about ZIO, it's a complicated story. I think it has a good story now with Z layers, but it's still using ReaderT. And if you read the documentation, it's not so clear if you're supposed to write your code as services and components wired entirely by Z layer, or if you're also supposed to wire some of them and providing them through a reader environment using the R environment in ZIO. And for me, there's an overlap in how you build your system. And it has this issue, a big issue for me is that you have the risk of exposing your implementation if you have something like make user 2, where you are effectively exposing the fact that this function is showing up its dependencies in its signature. So I'll be fast. And I think the important properties we want to preserve are encapsulation. That's really important. Have ways in whatever library or approach you're using to rely on interfaces, not on implementation, and have good ways of wiring your system. So in Haskell, I have a proposal for this. You can have a look at the associated presentation. But my advice to newcomers will be don't use anything fancy. Especially hide those dependencies. Make sure at some stage you can just expose those functions. And in Scala, it's very easy to do. You can have interfaces, traits in Scala. You can use case classes to just expose as members your dependencies. So those dependencies are hidden from anyone using the group chat trait. And you can have a place where you wire everything up. And it's a very easy way to grow your application. And if you have a good IO data type, you can write pretty good services and you can use functional programming to do some very neat stuff. It's a very easy way of doing things. I mean, it's so easy. I should market it right now. Well, of course, it's not so easy. There are other issues we need to consider once we grow those systems. And for example, I want to point out that we still have a use for monad transformers. And for example, where we need to propagate request IDs across our system, the only way to do this is to have some sort of reader effect in our stack. So this is a place where the R parameter of ZIO comes really in handy because there's no way to implement this using a component, because that is purely depending on the call context of each call. So we need a reader effect in this situation. But otherwise, we can write nice scalable systems with very, very simple concepts. We don't have to use crazy techniques. So that's the end of my rant today. Let's talk in the chat. And probably I can stop here, because the rest I'm about to say is about techniques that many people know about here. If you are interested in functional programming, it's about using functions. Even at large, now we can do ACID transactions on streaming, on functions. We can use types using generics, polymorphism. Type classes are a wonderful way to get more modularity in our systems, or there are new techniques about higher kind data. And as the last few words, because I'm really over time and I'm sorry about that, I'm leaving you a few pointers about some nice stuff coming up in the future. One thing is variational typing, which is a way of introducing modularity in our systems across time, when things need to evolve across different Haskell versions or different Scala versions, for example. We can have type systems to deal with that now. And there's lots of research still going on modules, like in ML, for example. There's this thing called 1ML, trying to unify the module language in ML with the term language. Those things are actually two different languages into one language. And in Scala, there's the fact that Scala 3 is going to be based on some very sound theory now for objects. And objects have a nice notion of interface and implementation that has a sound theory now and sound theory of subtyping. So that's really exciting to see that programming languages now can promote modules based on some sound theory behind it. So yeah, one last word, last pointer. If you want to talk about modules, have a look at this paper, just introduction, because it introduces some nice distinctions about terms. When you talk about modularities, there are different aspects of modularity, and have a look at those distinctions between weak and strong modularity and small and large, because that will help lots of discussions you will have around modularity. I wish I had more time to talk about this, but I suppose I should end here today. We care about modularity. That's really hard to get there, but we have lots of tools to get there, and most of those tools, they don't have to be hard. So that's it for today. Thank you all very much. I would like to see you, all of you, accounts, but thank you.